Imagine the scent of perfume slowly drifting across a room versus the high-pressure hiss of a punctured helium balloon. Both involve gas molecules spreading out, but they do so through different physical paths. The perfume is an example of diffusion. This is the natural, unassisted mixing of molecules from a region of high concentration to low concentration. The balloon represents effusion, the forced passage of gas through a tiny hole under pressure. While these processes look different, they are both governed by the same underlying laws of molecular motion. To understand how these gases move, we have to look at the individual molecules, and specifically how much they weigh. In the world of kinetics, mass determines speed. Heavy, bulky molecules move slowly, while lighter molecules travel at much higher velocities. This relationship between a molecule's mass and its velocity is the key to predicting how any gas will behave when it's time to move. Thomas Graham, a 19th century chemist, was the first to turn this intuition into a precise mathematical formula. His law states the rate of diffusion or effusion is inversely proportional to the square root of the gas's molecular mass. The math contains a flip. If gas 1 is on top of the rate fraction, its mass must go on the bottom. This inversion reflects the physics. A larger mass in the denominator of the equation results in a smaller overall rate of speed. Let's look at a practical example using light hydrogen, with a mass of 2, and heavy oxygen, with a mass of 32. To find the relative rate, we place oxygen's 32 on top and hydrogen's 2 on the bottom. 32 divided by 2 is 16, and the square root of 16 is 4. Physically, this means for every 1 molecule of oxygen that escapes, 4 molecules of hydrogen will have already made it out in that same window. Let's try a theoretical problem. Suppose an unknown gas A is exactly 9 times heavier than an unknown gas B. Using Graham's law, can you determine exactly how much faster the lighter gas B will effuse? Pause the video now and try to solve the math before we reveal the answer. By placing the heavier mass of 9 over the lighter mass of 1, the square root yields a rate of 3. This tells us gas B is 3 times faster than gas A. It's important to remember that rate is defined as the volume of gas moved divided by time. Because time is in the denominator, a higher mathematical rate means the physical process is finished more quickly. Finally, consider the force behind the movement. Since effusion is defined as movement under pressure, the rate is directly proportional to how much gas is pushed. Squeezing the container increases the frequency of molecules hitting the opening, which directly increases the rate. Predicting gas behavior isn't just about the molecule itself. It's about balancing the internal mass of the gas against the external pressure and the time allowed for the process. Here are the 3 rules for your notes: the distinction between diffusion and effusion, the kinetic rule that light gases travel faster, and the formula that uses the inverse square root to prove it. Take a screenshot of this summary, and always remember to flip your variables when you set up your equation. Once you master the relationship between mass, pressure, and time, you can control the movement of any gas in any system.